We'll keep that deliverable around the mid-sem time, your mid-sem break, like after your mid-sem exams. Okay. क्या हो रहा है भैया? Start? Should I start? Okay. Alright, so let's start the third lecture. So for those who are not here, just summarize. We are keeping 30% marks for the mid-sem exam, 10% for a quiz which we'll take first week of February, and then 10% for a survey paper where you will summarize 10 to 15 or 20 papers. So that is what we are doing. Research papers where machine learning is used in your domain of choice, wherever you want to explore things. Alright, so let's start the lecture. Last week we started regression and we did what is correlation. What's the difference between correlation and regression? Sorry? Anybody else? Okay. Metrics are in both regression, also we are going to see metrics. What is the difference between correlation and regression? All blank? You don't remember a thing? He's saying yes. So correlation is where there is no relation between the two sets of variables you are trying to analyze or process. Regression is where one is the independent, other is the dependent variable. That is what we told last time. Then what we did was, besides the introduction, we talked about simple linear regression. Simple linear regression where x and y, x is the independent variable, y is the dependent variable. We said both are belonging to one-dimensional space, R1 and R1, then it's a simple linear regression. In that I summarized that you're trying to draw a line in two-dimensional or a hyperplane in n-dimension, and the equation of the line, how it covers all the points. So you find residue by projecting on the line. You do that in a least square sense, which we motivated last time. And then once you have the residue function, you find its minimum value, because you want all the points to be as close to this line as possible, right? To do that, we said you're going to go back to your calculus. You'll take the first the derivative and make it equal to 0. You'll get candidates for minimizer. You got alpha and beta last time, which you did it in your homework, but those are still candidates for minimizer. To get the actual minima, you have to take the second derivative in an n-dimensional sense, that is the Hessian, those who were there yesterday. And then if it's the point you found by making the first derivative equal to 0 satisfies the Hessian positive definite, then it is a minimizer. And if your Hessian is positive definite over all of the space, then it's a convex function. The minimizer, which is a local, becomes a global minimizer, right? So this is what we talked in simple linear regression. And this is what I was just reminding you. So I've written a note here that alpha and beta, which you get by making the gradients or partial with respect to beta equal to 0, partial with respect to alpha equal to 0, the gradient equal to 0, will give you a candidate for minimizer. This is what is written here, the first point. Then you have to check the second derivative. It will be the Hessian. It will be a two-dimensional matrix in this case. Why? Because you've got only alpha and beta. It's a function of two variables, right? Recall y is equal to mx plus c, and it is beta xi plus alpha. So the alpha and beta are the two variables. So the Hessian which you will get will be 2 cross 2 matrix. CS undergrads know it, others we just did it yesterday. We computed the Hessians. Did you went over and did the problems in the PDFs? Yes or no? Do it, I mean, it's for your own good. And then finally, if the problem is, so this positive definiteness of the Hessian, have you done the homework too? Okay. The positive definiteness of the Hessian has to be checked at the point which you have found by making the gradient equal to 0, and there it should be positive definite. If it is positive definite everywhere, then the function is convex. This also we studied yesterday. In that case, the global minima becomes a local minima becomes a global minima. Everybody okay? So what we started last time at the end was multiple linear regression. So these parts which we have not done for this smaller simple linear regression, we'll do it for the multiple linear regression case, which you will see today. So in case you were lost a little bit on this, it will get more clearer as we go along. Okay. So this is what I'm talking about, multiple linear regression. In this we are saying that X is, of course this end, the data is endpoints X, endpoints Y, which are given by the superscript, and each of the X is a d-dimensional vector. So the dimension of the problem is d. So the number of points are n, which are the superscripts. The number of dimension of every point is d, which we write as a subscript or below the value. But we're still working with the labels or the dependent variable to be one dimensional. So it's still R1. That's why it's called multiple linear regression. If R, you can make this also m dimensional, m for monkey. In that case, this will be multivariate multiple linear regressions, because you've got the domain range also changing. Okay, so to do that, we first wrote h theta xi, which is theta naught, theta 1, x1, theta 2, x2. So you can see the subscripts x1 to xd are the dimension. The superscript, I have just put it for the first point. Could be for the second point, could be for the nth point. In the previous case, which was the simple linear regression, theta naught was alpha, theta 1 was beta. Y is equal to mx plus c, which we wrote earlier, right? So now your h theta is going from a d plus one dimensional space. Why? Because they are theta naught to theta d. Those are the unknown variables. Yes? Everybody with me? And it's going to a one dimensional space. So you can write it as a summation of theta j, xj, xi. This also we saw last time. Now you write the residue function. You'll write the residue function again in the least squared sense. So you're taking the difference between the predicted point by the function you are approximating minus the actual value at I being the subscript at that particular data point and squaring it. So again it goes from a d plus 1 to one dimension space. So this is where we had stopped. Now we're going to start how to solve this. To solve this, we'll go back to the simple linear regression case and do what we did earlier. Make gradient equal to 0, find the candidate for minimizer, compute the Hessian, check whether it's positive definite, check the Hessian positive definite over all of space, is it convex or not. All those three things we're going to check for this. What it will turn out that it is more difficult in this multiple linear regression case to solve it by this closed form solutions, this solution where you're trying to find the gradients in Hessian, because there is an inverse of a matrix involved. So which means that you can either do it analytically by doing gradients, Hessian and so on, or you can do it numerically. Numerically is where you iterate. Those who have done numerical methods second year, everywhere in India or anywhere you are, this is taught. For example, applying the Newton's method to solve a non-linear system of equation. You start from an initial guess, you iterate. So that's a numerical solution. So here also we'll do two things. We'll analytically find the solution today. We'll numerically find the solution and we'll see what are the advantages of those. So that's where we are going today. Okay, so that's what I've written here. Closed form solution and numerical solution. Everybody with me where we are going? This was a summary of what we did because you may have forgotten. So I'll start today's lecture. So today's lecture we start with the closed form solution. So if you see this where we had stopped, I'm trying to write this h theta xi more explicitly. What is my h theta xi? It is this guy. Or summation theta j xi xj of x of xj of I, subscript I. So what I'm trying to tell is this thing can be written in this form. So wherever in my slides you see written work, which means that I'm going to work it out on the right side on the board. So you can see the scribble part. So let's start this. So we are first looking at the closed form solution. At the back, everybody readable? Slides, no, not too small or big. Hai? So what is h theta? So here h theta of xi at the ith point is theta naught plus theta 1 x1 ith point plus all the way till theta. What's the final theta? Theta d. Okay, I'm just checking you're not sleeping. xd, it's the d8 dimension, xi. Right? That is what is written in the first line. So what we could do is we can write this as theta naught, theta 1, theta d as a vector, and I can write this guy as x1 I, x2 I till xd I as another vector. Sorry. Good. So this will be 1 and this. Correct? Everybody with me? It's just writing the inner product of two vectors, theta naught, theta 1, x1 till theta d xt. So this can be written as theta if you want to write it as a transpose as a vector, and then x of I. So here theta and x both are vectors. In the slide you can see that it's made bold to emphasize that it's not a scalar, it is a vector. Here I can't do it. I can start putting, typically what I do, I put arrows to define vectors, but that may get more complicated because of the indices coming around. So we'll just make it slightly bold. Everybody with me? Okay. Now what we do is, you'll see in a minute why I am writing this and why I am writing in this form. The next slide talks about writing the h theta, all of it. So this is one thing. Now if I have to write h theta of x, you can see theta is again a vector, x is again a full vector. You will want to write this as h theta of x1 all the way till h theta of xn. Correct? Everybody with me? Because I just wrote h theta xi. Now I'm taking all the x1 to xn and putting them in a row format. I'm just playing around with weight matrices in here. So we're going to write this further. So if I have to write this, this would be, what was h theta x1? It was theta naught plus theta 1 x11 till theta d xd1. Correct? This was the first at the x1 point, superscript 1, all the dimensions of x. When I have to write it for at the nth point, this is theta naught plus theta 1 x1 nth point till theta d xd nth point. Everybody with me? So I want to write it in a product of a vector and a matrix, which is shown on the slide. That's why I'm doing it. So what I could write this as, this could be written as 1 x11 xd1 1 x1n xdn. And I'll pull the thetas on the outside, theta naught, theta 1, theta d. Is everybody with me? 1 into this, this into this, into this, this into this, this into this, plus this into this, plus this into this. I've just written that, which means that this is nothing but, if I call this guy as an X matrix, and this we already know is theta. We have defined this as theta here. Correct? So typically in mathematics, when we write matrices, we write them in capital English letters. When I am writing, typically I write scalars in Greek letters and I write vectors in small English letters. Typically that's the case. But here X is a matrix, it's a larger capital. Theta, although it is a Greek letter, but I'm making it bold to tell that it's a vector. Is that okay? So it's a product of a matrix times vector. Everybody with me? These two play around which I have done. Now we'll go back to our residue function and try to put these there. That is the goal. Okay. So let's look at the cost function or the residue function. Okay, so the residue function, you're saying j theta is 1 over 2n h theta xi minus yi, where summation I going from 1 to n. This is written as the first line. And you're doing it in a least square sense. H theta of xi, correct? Now h theta of xi, what have we written earlier? It is theta transpose xi. So I'm going to substitute that. So this will be 1 over 2n summation of I going from 1 to n. Instead of h theta xi, I'll write it theta transpose xi minus yi. Everybody with me? This is what we just computed. Now we're going to simplify this further. So what I'm going to do, don't look at the slide here, just look what I'm writing. So I'll write this as 1 over 2n summation of I is equal to or let me write it as so I could write it theta transpose x1 minus y1 square plus all the way till theta transpose xn minus yn square. You can put the bracket outside to tell this. Nothing changes. I've just expanded the summation. But I could also write this as 1 over 2n theta transpose x1 minus y1, one element, then all the way till theta transpose xn minus yn, the last element one vector, and then I put a column vector theta transpose x1 minus y1 all the way till theta transpose xn minus yn. Does it change anything? This into this is this square, this into this is this square. So you're just writing it as a inner product of two vectors. Yes or no? Okay. All right. So now what is this theta transpose x1 to yn? Recall this. So what I could write, let's say I had to write this guy. So this is theta transpose x1 minus, so I can write this as theta transpose xn minus y1 till yn. I can write this? Yes or no? I've just separated the two vectors, theta transpose x1 to xn and y1 to yn. I've separated them. Now what is this guy? Theta transpose x1 to xn. It is this guy, h theta x, which is nothing but capital X times theta. Can everybody see? You just theta 1 to theta d added, same thing is happening, theta 1 to theta d added, theta naught plus theta 1 to for the xn point. So this is nothing but x theta, theta again I'll make, this all thetas are bold because they're all vectors, hai na? And so are the x's. And minus, we'll call this, these y's are what? y1 to yn, these are scalars. These are made bolds. But these are not, because y is one dimensional. We're talking about not multivariate. The range is still 1. So this is minus, now this becomes a vector because I'm putting y1 to yn. So this is x theta, this is minus y. Everybody with me? So hence, your whole thing, j theta becomes what we showed you for this guy. This is just the transpose of that, because you're multiplying the two. Can everybody see it? So this is nothing but 1 over 2n. X is a matrix, so it doesn't matter. I'll make this bold. Theta minus y bold vector transpose times x, again bold, minus y bold, this. Everybody with me? Why did I do all this? I did because these summations were creating too much trouble for me. There were too many indices to worry about. There was the dimension index, which was the j going in the subscript, and there's the point or the data point index going in the superscript going from 1 to n, I. So I wanted to just abstract everything out and get it in terms of matrices or vectors. Everybody okay? Now what will I do? I'll do the necessary and sufficient conditions which we talked about yesterday. So we'll do gradient of this, make it equal to 0, check for the Hessian and check for the convexity, right? So all that we'll do. To do that, it's done on the next slide. Let's first expand this. So once you expand this, it will be 1 over 2n. When you take transpose of product of a vector matrix or matrix vector, they swap positions. Right? So x theta transpose will be theta transpose x. So which means this multiplied by this would be theta transpose x, x theta. It's the first term. Minus, what will be the second term? Let's say I'm doing this, so this will be y transpose x theta. Minus this times this will be theta transpose xy. Sorry, 1 second. This y transpose x theta, then this will be theta transpose x transpose times y, and then it will be plus y transpose y. हाँ sorry, जल्दी में किया. ठीक है? Everybody okay? So now what we'll do is, first tell me what are these. This can be written as, first of all, what's the dimension of y? Y is n cross 1, correct? So y transpose is 1 cross n, so this is 1 cross n. What's the dimension of x? What is the dimension of x? They are n rows and they are d plus 1 columns, correct? So this is n cross d plus 1. This is your x, and what is your theta? Theta is again just d plus 1 cross 1. It should match also, so you don't have to think too much. I'm just going back and telling you. Now when you multiply the whole thing, this is a scalar, which means that this term can be written also as y transpose x theta. If you do a transpose of a scalar, it doesn't mean anything, right? It's just a scalar. Transpose are for vectors or matrices, correct? So this term can be written as y transpose x theta, means these two terms will add up, correct? So this is 1 over 2n. This is on the next slide, so you don't have to write down. So this is theta transpose x theta minus 2 times y transpose x theta, or if I want to write this in terms of the first term, then I can, in terms of the second term, then I can also write this as theta transpose x transpose y minus or plus y transpose y. Everybody with me? ठीक है? यही हो रखा है नेक्स्ट स्लाइड में, what all I just discussed. You have to do gradient of this, they are 1 cross 1 and this becomes this. Now I have to do the gradient. I'll just stay in the previous slide so that you don't start reading. So we'll do the gradient of this, which means I have to do the gradient of this guy and gradient of this guy, correct? So I have to do gradient of j theta is equal to what? So which means if you do gradient with respect to the third term, it will be 0. Why? Because gradient is with respect to the thetas. Those are the unknowns. X is the known. X is the data point. Recall. Thetas are the unknowns which are defining the equation of your hyperplane. X's are the given points, right? So X is known, theta is not known. So the gradients are with respect to the thetas here. Everybody with me? So I'm going to do partials now. So if I'm going to do partial with respect to, so this gradient of j theta, third term will be 0. Now I have to do gradient of j theta, the second term. What will that be? So I'm just telling you, we did that as an optimization. So this is gradient of theta transpose x transpose y. This is my second term. Yes? Everybody with me? So what is this? I can call this, what is the dimension of this? D plus 1 cross n, n cross 1. So d plus 1 cross 1. So it's a vector. Let me call this as a vector z. So what I'm trying to do is gradient of theta transpose z. All this is bold, by the way. They are vectors. So just keep that in mind. So which means that I'm going to do gradient of theta 1 z1 all the way till theta d. Sorry. थीटा नॉट से स्टार्ट होगा. थीटा नॉट जेड नॉट प्लस थीटा डी जेड डी. Correct? Everybody with me? Now what is gradient? D over d theta naught till d over d theta 1. This is what gradient means, theta d. You're taking partials with respect to everyone. So if you do d over d theta of with respect to theta naught, what will you get? Sorry? Z naught. To do theta 1, you will get Z1. With respect to theta d, you will get ZD. So the whole thing will be Z. The whole thing would be X transpose Y. I did this for the non-CSE people. I would have expected the 4th year computer science to tell me this, because in optimization we did this so many times. Who are CS undergraduates? Raise your hand. Do you agree with me? We did this many times. I wanted you to tell me this right away, that if it's theta transpose a vector and take a gradient, you just get that vector out. Correct? Okay, now this was the second term. This is the first term. If you do it with respect to the first term, what do you get? Now the CS undergraduates want to tell me. So gradient of j theta with respect to the first term is equal to gradient of theta transpose x theta. Does anybody remember this? अरे CS undergraduates, अभी तो एक ही साल हुआ है, forgotten everything. So this is worked out in the homework. So what you do is, it's difficult to do it here. It will take 10-15 minutes to work this out in a general case. So I've done it in the homework. You go and check. What happens is you get It's basically a square of the theta which are coming, and there are 2 which will come in front. You take a 2 cross 2 matrix and work out. Have you done that, Kuldeep, in the homework? Okay, I'll show you the homework where it's worked out. So what you get is 2 of x transpose x theta. This is what you will get. You will follow the same steps like I did for the second term, except that you do it for a smaller 2 cross 2 matrix. First do that, and then you can generalize it for an n cross n matrix. Or in this case, x transpose x, what's the dimension of x transpose x? Huh? X transpose x becomes 1. What's the dimension of x? N cross d plus 1. X transpose becomes d plus 1 cross n times x n cross d plus 1. It's a d plus 1 cross d plus 1 matrix. So I'm saying don't do it for the general, do it for a 2 cross 2 matrix, and then you can easily see that this will come out. I'll show you in the homework, it's worked out. Hai na? Okay. So now we're going to take all the gradients and put that in the original gradient of the j theta which we wanted to find. Everybody with me? Yes or no? Okay, so we'll go to the next slide. So now you can see this is what I've written. I've written homework 2 also, which means that this is worked out in homework 2. You take the gradient of this. So there was a 1 over 2n here, so which we are ignoring. The 2 which will come out from the first term will cancel with this 2. There is a 2 coming here which will cancel out with the 2 here. There was a 2 here which will cancel out, and this term was anyways with respect to 0. So once you take the gradient, you will ref with x transpose x theta minus x transpose y, which means that this term and the second term was with a 2, so I should have put a 2 here, 2 and carry a 2, carry a 2, carry a 2, carry a 2, so that this 2 doesn't bother you. And the 2 will cancel out with a half in front. The n will not matter because it will go to 0. You're making gradient of that equal to 0. And the third term anyways is 0. So you'll be left up with, so the gradient of j theta equal to 0 would imply, so you've got x transpose x theta. This is 2, we carry 1 over 2n minus 2x transpose y plus 0 equal to 0. The n will vanish, the 2 will cancel out. So you're left with x transpose x theta is equal to x transpose y. Correct? What is your x transpose x? We just told you it is a d plus 1 cross d plus 1 matrix, which means it's a nice square matrix, which means that you don't have to go to pseudo inverses at this stage in this one. We'll do that when we go to regularization, which is the next lecture. That's why I told you about pseudo inverse, those who were there, but not at this stage. So then your theta becomes x transpose x inverse x transpose y. This is a vector which is d plus 1 cross 1. Right? So this is the candidate for minimizer. Why? Because we have just taken the gradient and make it equal to 0. Everybody with me? Okay. So now what we'll do, this is what I've written here. Above is a necessary condition. I forgot condition here. Condition for minima, which gives us the candidate for minimizer. Now we'll do the same thing. Check for the second derivative whether the Hessian is positive definite at the given point. Finally, is the problem convex? Hessian is positive definite everywhere, so the global local minima becomes global minima. So now let's go back and see the homework 2. Please work it out for yourself. Although I'm going to just run it over for you. Any questions at this point? You guys are not asking any questions. I'm not teaching well, it means. No questions? Sleepy, joke, wake you up, anything? Okay. Alright, so before I start the numerical, so why do we need a numerical solution? Because this guy may not exist. It could be that all matrices, even square ones, are not invertible. That you know from your linear algebra. If it is rank deficient, that's why I said yesterday, those who were there, go back and revise your linear algebra if you can. If it is rank deficient, it's not full row rank, it's the rank of the matrix is not d plus 1 in this case, then it will not be invertible, which means that the inverse may not exist. You may be lucky to numerically find an inverse, but it's not guaranteed to have an inverse, which means that you'll have to fall back to other techniques, and that is where the numerical solution comes, which we're going to talk next. But before I do that, I'm going to show you the homework too. Okay, let's go back. I've not checked. I asked Kuldeep to make it, so I hope. In case it's not done well, then we'll see tomorrow, है ना? कहाँ चला गया? Okay. Okay, so I think some parts we have worked out. Let's see. Kuldeep, I said don't write this as j over j theta, but never mind, we'll fix it later. So this is what we have already seen. We have seen this, we have expanded this out, and then I've shown j theta. You have to do it with respect to all of them. Hurry, nahi. I'm sorry, this is not worked out well. I'll fix it and upload today, then you can take a look, है ना? So where were you? Okay, so and by tomorrow I'll show you, है ना? So what we have not done is, when you take the gradient of this guy, so what we have not shown is, when you do the gradient of the first term, you get 2x transpose y. When you do it for the first term, you get 2x transpose x theta. What you have done wrong is you have pulled the theta transpose theta away. You can't do that. X transpose x is a matrix. So that is why. So maybe I'll just show you what I had uploaded. Then maybe it will make sense. So this is what I had written here, that I think the computer science people can work this out, but I'll upload it. Once you do the gradient, you'll get this term. When you do the Hessian of this, which is written as d2 over d theta square, don't look at this, it should be written as Hessian. That's why I wanted him to correct and upload. You will just get x transpose x. X transpose x, is it dependent on theta? No. Which means, is it positive definite? Yes, we showed that it is positive semi-definite. We show that u transpose, when you multiply with x trans, first of all, when you take the Hessian of this Jacobian of this gradient, which is the Hessian of j theta, you get x transpose x. We'll work it out and put. Once you get x transpose x, let's go back to the slides. Okay. So when you look for the sufficiency condition, we need to check if the Hessian is positive definite at the given time. The first thing which we saw was, where did that open? Opened here. Is that the Hessian is x transpose x, it's independent of theta. Now we have to check whether it's positive definite or not, positive semi-definite for convexity. So once you do is, you multiply with the vector u non-zero from left and right, and you get that it is greater than equal to 0, so hence it's positive definite. So hence it is a minimizer, it is independent of the point, so it is a convex function and it is a global minimizer. But I'll work this out and go over again tomorrow. So just so that the chain of thought doesn't stop, I wanted to go over it. Okay, so the browser closed, we'll open it again. Okay, so this is what homework 2 will go over again. Then now let's look at the numerical solution. So this is the second part. The numerical solution goes like this, that they've shown it for the two-dimensional case, theta naught and theta 1. How many thetas we have? D. d plus 1, theta naught to theta d, right? So we're not showing it. This is a hypersurface in that case, and you will start somewhere and you have to reach the minima. So what we do is we apply something called as the gradient descent approach. Now those who did optimization would know steepest descent we did. It's the direction of the negative gradient that you go. Those who have not taken it, I'm telling you now that like in the Newton's method for solving nonlinear equation, you start from a guess and you move towards the solution. Similarly, you start from, let's say you're trying to minimize f of x, going from n-dimensional domain to one-dimensional range. You start at x0 and then you do an update. This is an algorithm called the gradient descent method, where the direction vector is given by the negative of the gradient of the function at that given point. Everybody okay? Yes. So now we're going to apply this to our context. So that is what we're going to do. So we're doing this repeatedly. So theta j is theta j minus alpha gradient. This is for every theta, theta naught to theta d. That's why the partials is written here. So if this was your j theta in one dimension, the red line is defining the gradient or the derivative, because now it's in one dimension, and alpha is deciding how much you want to go that direction. So you're here, you go a little bit, then you go here, you go a little bit, then you go here, and then you will reach the minima. That is what it's trying to tell you. Okay, so now let's work it out. So what you're saying, we want to do partials of this with respect to theta j. This is it readable or too small? Small, right? Make it bigger then. We don't need to write here because it's written on the slide. Now readable? J theta was this, which by now you know, the difference between the predicted value and the actual value for the ith point, and difference squared and summed, the least square sense. So we're going to do that. Okay. So what is h theta? It is nothing but theta naught x1, theta 2, x2 till theta d xd for the ith point, which is the superscript. We substituted this. Everybody with me? Now when I do the partial of this, what will I get? If I take this theta j and do the derivative of this, what will I get? First thing is this 2 will come in front, and then you will take the derivative of the inside, right? dx square over dx would be 2x, right? So it will be 2 and then the derivative of the inside function. So we'll write that down. Everybody with me? This term came in front, and I have to take the derivative of the inside term. Yes or no? Correct? What's the derivative of the inside term? xj. Everybody agrees? It will be theta naught x1, theta 1 x, theta naught x0, theta 1 x1 till theta d xd, and you differentiate with respect to theta j. So which means that xj will be left and all the other thetas will be 0. Should I write it down or is it clear? Clear? Okay. So the next slide writes it down. The derivative of this term is nothing but xj. Remember, the I am not touching. The I superscripts is remaining the same because it's the summation over all the points. So that summation is all along not being touched. Everybody with me? So this is what I just did, no? Theta naught, theta 1 x1, and then theta j xj, and you do it with this to theta j, so you're left with xj. Correct? Okay. So now this is the final equation for the gradient descent method. It is theta j minus alpha. This is the gradient. This is the gradient which we found on the previous stage. This is it. This I am writing it as h theta xi, nothing else on this. Correct? Everybody with me? So the numerical solution is not guaranteeing you anything. It's not guaranteeing you whether it will give you a local minima or not, because it's just at every point taking the gradient and going towards it. It has a drawback that it could get stuck somewhere in a loop and not reach. So when will you stop? What is your theta? Theta is theta naught to theta day. When you see that the theta values are not varying too much, this is typically what we do in a numerical algorithm. Whichever variable you're trying to find, when its values don't change too much, you stop. How do you check the values don't change too much? It's a vector. You find the norm of it, the 2 norm. What is the 2 norm of a vector? It is the sum of square of elements. So norm of x square is nothing but x1 square plus x2 square plus xd square. So what we'll do here is you'll take the difference between the theta new at the new step and the old step. These are all vectors. Find that 2 norm. If its value is less than some value, let's say epsilon minus 3, you stop. The norm is written here. Everybody with me? Okay. So I think the rest of the slide is, if you got this point, what I've done is I've given you a closed form solution by making gradient equal to 0. The Hessian part we didn't compute, but I told you that the Hessian of that will come out to be x transpose x, which will be positive definite everywhere. It will be a minimizer rather than a candidate for minimizer, and x transpose x is a positive definite over everywhere, so it's a convex function, so it will give you a global minimizer. But the problem with the closed form solution was that x transpose x inverse had to be found. That inverse may not always exist, so you will fall back to the numerical solution where you will apply the gradient descent method, where you start from a particular theta and go in the negative gradient side and keep coming down. And this is what the iterate for that is. Now how this proceeds, I have a couple of minutes, I'll finish the rest of the slides because they are not too many. It's not too thoughtful, the rest of the slides. So it's giving you an example. So let's say red were the points, data points which are given to, and we are working in a 2-dimensional space. So this is your x, and this is your y, which is the price, and the equation h theta, which is the difference between the predicted and the actual value, is given by this line. So when you draw the j theta, the contours of that, what are contours? Where the function has same value. So these contours are outside a larger j theta, the residue function, and as it gets smaller and smaller, it's a lesser value of the residue function. So initially you did an initial guess of theta naught to be minus 900 and theta 1 to be 0.1. Let's say, this comes from experience. This is domain person will tell you where to start. We don't know where to start, but let's say we have this and then we apply the first step of the gradient descent method. The first step of the gradient descent method means applying this iterate. So this is theta naught for the first point, theta 1 for the first point, and this is be theta naught for the next point, theta 1 for the next point, right? So you're doing theta naught, theta 1 initially and next. What is that? So once you do that, you get a line like this. You get slightly better and your point moves more towards the minima. The minima is going to be here because this is where the j theta has the minimum value, towards the center where it's almost 0. So the next few slides is just moving towards the minima. You can keep looking at the red point which is moving in the line which is getting better. I'll show you the last one. Every iteration, how the theta naught and theta 1s are changing. So this will be finally where it will stop. You can see you started with a line somewhere like this, but now this is the best line which you would have intuitively guessed because points are all centered around this. You have to project on this line and take the minimum of that in a least squared sense. So this means that once you get this line, it will reach here. Okay. So the choice of alpha here is very important. If alpha is too small, this is showing in a 1-dimensional setting, by the way. We're not showing in an n-dimensional setting. If this was the curve, you're going very slowly. If you increase alpha, it may switch between. So alpha is crucial. It is written here. It's written somewhere that if you want to see how gradient descent is working, you should print the value of the value and see whether it's decreasing or not, and it's not flipping between the sides. So the last slide is the difference between the two. The closed form solution is good, not alpha. It does not always work because the matrix may not be invertible and it's expensive. I'll work this out next time why it's expensive. Here you need to choose an alpha. It always works and it's cheaper, but it's not guaranteed to find a solution. So that's a problem here. Okay, so we'll stop here. Tomorrow we'll do regularization, but before we do regularization, I'll go back to homework 2 and show you why you get the Hessian of the J theta as X transpose X, why it is positive definite at that point and positive definite everywhere. Any questions? Hey, please ask questions. No, I don't feel good. I feel that you're not getting it. Stop me. Don't be shy. Okay, thank you.